Hello, this lecture is on first order systems in series part 2. In the previous lecture, that is part 1 of the same topic, we saw that when two first order systems are connected in series, they can be either non-interacting or interacting. We also saw what is the meaning of these two, interacting and non-interacting, that was explained in the previous part. Now we will see more about non-interacting systems in series. We will see about non-interacting system series in detail. So now how do we write the transfer function of non-interacting systems in series? Suppose let us take two non-interacting systems. I am just taking general. Systems means general. How do you write the transfer function of non-interacting systems in series? The overall transfer function of two non-interacting systems in series will be equal to the product of the individual transfer functions of the two systems. That is, if you have two non-interacting systems in series, we know the transfer function of each, first system and second system. Now if you want to know the overall transfer function for the two systems together, it will be the product of the individual transfer functions of the two systems. Now you can generalize it to more than two systems in series. This statement can be generalized to more number of any number of systems, n number of systems in series. Let us consider n first order systems in series. We have the figure shows n first order systems. The first one transfer function is k1 by tau 1 s plus 1, next k2 by tau 2 s plus 1, and so on. The nth system has a transfer function kn by tau n s plus 1. The input to the first system is x0, output is x1 for the first system, and the last system input is xn minus 1, output is xn. So if you see individually, the transfer functions for each system are shown here. This is x1 by x0 s is k1 by tau 1 s plus 1, x2 by x1 s k2 by tau 2 s plus 1, and so on. The last one xn by xn minus 1 is kn by tau 1 s plus 1. Okay. Now if you want to find the overall transfer functions of the n systems together, so this can be found by the rule stated earlier, that is the product of the overall transfer function of the n system together. The overall transfer function of the n systems together will be equal to the product of the individual transfer functions. So the overall transfer function will be equal to the overall transfer function xns by xn by x0. xn by x0, the overall transfer function, will be equal to the product of the individual transfer functions k1 by tau 1 s plus 1 into k2 by tau 2 s plus 1, and so on. So the overall transfer function is the product of the individual transfer functions as shown here. The overall transfer function is the product. This pi stands for product of ki by tau I s plus 1, I varying from 1 to n. So this can be done for not only tanks, any first order system, any number of first order systems in series. As long as they are non-interacting, the overall transfer function will be equal to the product of the individual transfer function. Clear? I hope it is clear. Now let us C for let us see for two non-interacting tanks. We will go to from general systems. We will go more specifically to tanks, two non-interacting tanks. How do you write the transfer function of two non-interacting tanks? Using the above rule, you have to recall the figure of two non-interacting tanks in series from the earlier lecture. So if you see that figure, H2S by QS, here if you see Q1, Q is the inlet to the first tank, Q1 is the outlet from the first tank, Q2, which is not shown here, Q2 will be the outlet from the second tank. H2 is the height of the second tank. So we are relating the height of the second tank to the inlet flow to the first tank. Okay. So H2S by QS. Please read this along with the figure of two non-interacting tanks shown in the previous lecture. So the symbols are, the notations are as per that. The second tank H2, height of the second tank, height of the liquid level in the second tank, height of the liquid level in the second tank H2, Q is the inlet to the first tank. This is the overall transfer function. So that is equal to, this is the transfer function of the first tank, this is the transfer function of the second tank. So you can simply multiply here, Q1 and Q1 can cancel. So it is the overall transfer function of two tanks in series will be equal to the product of the individual transfer functions. So now, what is the product of, what is the transfer function of each tank? Q1S by QS and Q2S, H2S by Q1. So this is the transfer function of the first tank. Q1S by QS is 1 by tau 1s plus 1. Okay. Recall from the previous lecture. Q1S by QS is 1 by tau 1s plus 1. Tau 1 is a time constant for the first tank. Now for the second tank, H2S by Q1S is R2 by tau 2s plus 1. Here we are relating H2 height with flow rate. So the numerator, the gain is the resistance R2. So tau 2 is the time constant of the second tank. So this is the transfer function of the second and this is the transfer function of the first. So the overall transfer function is simply the product of these two. Overall transfer function is the product of these two, which is this R2 by tau 1s plus 1 into tau 2s plus 1. Okay. The overall transfer function of the two tanks in series, two non-interacting tanks in series, is equal to the product of the transfer functions of the first one and the second one. That is R2 by tau 1s plus 1 into tau 2s plus 1. Okay. Now that we know how to write the transfer function of these two non-interacting tanks, let us see the dynamics. Simple. Let us consider a step input being given to the inflow to the first tank. This is the overall transfer function. Just now we wrote G of S H2S by QS equal to R2 by tau 1s plus 1 by tau 2s plus 1. Now let us consider that the inlet flow to the first tank is given a step input. Okay. The inlet to the first tank is given a step input. This is the step input of magnitude m. So find the transfer function. Find the Laplace transform of Qt is Qs is m by s. So substitute this Qs into this and find out what is H2s. So H2s will be equal to Qs multiplied by this, that is Qs into Gs. Qs into Gs is m by s into R2 by tau 1s plus 1 into tau 2s plus 1. Now if you invert this function, invert this Laplace transform, you are going to get the response of two non-interacting tanks. You're going to get H2T. That is how the height in the second tank is going to vary as a result of this step input. Okay. So you are given a step input to the inlet flow to the first tank, and as a result how the height in the second tank varies. Okay, that is, you see, this is first tank, this is second tank, right? They are connected. Q, here is you are giving a step change here, you are giving a step change here in this inlet to the first flow, and as a result how this height 2, so this is H2. So this is Q. So you give a step change here to the first tank. Okay. You give a step change to the inlet flow Q, that is this. Okay. And as a result, because of the step change in inlet flow, how the height H2 is going to vary, that is given by this equation. So this H2T is nothing but the Laplace inverse of this. Okay, this is nothing but the Laplace. If you take inverse, you get this. Take L inverse of this function, whole function L inverse, Laplace inverse. So Laplace inverse of this is this function H2T by MR22. So as a result of step input to the inlet flow to the first tank, the outlet in the second, the height in the second tank, height of the liquid in the second tank is going to vary by this equation. So this equation is the response, step response of these two non-interacting tanks. Step response of two non-interacting tanks. Now let us see this graphically, how this behaves. How do you interpret this equation? So if you show the graph, you can plot, you can know more. So we'll see step response of n first order non-interacting systems in series by means of a plot. That is the previous equation what we had derived earlier in the last section, in the last slide, the response equation, that is this equation. If we plot this, how does it look? Okay, so this is a step response general, not only for tank. So this figure shows for any systems, any number of any system, whether it's a tank or any other first order systems in series. The general nature will be like this only. So if you plot the previous equation for two tanks, this y-axis will be H2T by MR2 for plotting for two tanks. Suppose you are plotting for two tanks, as in the previous case, this y-axis will be h2t, y will be equal to m, what you have derived in the last, h2 by m r2. So if you plot for two tanks in series, that will be this equation, this graph, this one. Okay. So the previous equation which you derived step response of two non-interacting tanks, that is h2 by mr2 equal to some big equation we got in the last one. So that will be, if you plot this, it will look like this. And y-axis will be h2 by mr2. The nature of the graph will be the same, whether it is two tanks or any other two systems in series. Okay. So that is why it simply says step response of n first order non-interacting systems, not necessarily tanks, any system. Okay. Now this figure also shows a single, n stands for number of first order systems in series. N stands for number of first order systems in series. N stands for number of first order systems in series. So when n equal to 3 means, suppose you put 3, first let us come to 1. 1 means there is only one system, single first order system. So what is the step response? This figure shows the step response of a single first order system in series. This figure shows n equal to 2, step response of two first order systems in series. And this shows for three first order systems in series. Just for comparison, I have given for one system, two systems and three systems. Now let us take one system and two systems in series and compare them. So what do you find? So for two n equal to 2, that is two first order systems in series, which is plotted by the equation you have just now shown, you find that at 0, the slope of the curve is 0 at the origin. Okay, the slope of the curve is 0 at the origin. Whereas for a single first order system, the slope at the origin is the highest. So this was discussed earlier, we have seen earlier also, that is when you have only one first order system, the step response, if you plot, the response will begin immediately at t equal to 0 at highest speed. So for two systems in series, this equation, if you see this equation, the slope of this equation at t equal to 0 is 0. That is, the slope of this equation at the origin is 0. So that means this, when you plot this, it will not begin immediately at t equal to 0, but only after a certain time. So there will be a slight horizontal portion at t equal to 0. This is the response of, I repeat, the response of two first order systems in series does not begin immediately at t equal to 0. So there will be a slight horizontal portion, very slight, which is not very much visible here. Here. So only when we zoom in that portion and we plot a bigger magnified graph, then you will see that this portion for this response of two systems in series, this graph will show a horizontal portion at t equal to 0. So the response begins only after a certain time. So there will be certain lags before which there will be certain lag. Only after that the response begins. This lag is known as transfer lag. So this transfer lag will always be present when two or more systems are connected in series. Okay. So transfer lag will be present when two or more systems are connected in series. So, and this lag will increase as the number of systems in series increases. For one system there is no transfer lag. For two systems there is a transfer lag. The response begins only after a certain time interval, certain time, however small it be, after the disturbance takes place. For three systems, that lag will be still more. If you put four systems, the transfer lag will increase. So the transfer lag is a lag which is always present when two or more systems are connected in series, and that will always increase when the number of systems are increased. Okay. So this is about the dynamics or step response of first order non-interacting systems in series. Okay. So a word of information about this equation which you had shown, or about the rule that the overall transfer function can be found by the product of the individual transfer function is a theoretically derived statement. It is not just a statement or not any assumption. It is not any assumption. It is not a just statement. It can be theoretically derived. Okay. So I hope you have understood. If you have any comments, if you have any questions, you can leave that in the comments. Please share this to your friends if you like it. And we'll have more to continue. We'll have more coming up. The next part we'll see about interacting systems in series. Okay. Till then, see you.